Hi everyone. I'm going to present our paper Discovering and Mitigating Biases in Clip-Based Image Editing. I'm Mehrab from Adobe Research, and my co-authors are Krishna, Kushal, and Ritwik from Adobe Research, and Gary from UC San Diego. Now, we are all familiar with image editing. Here I'm showing an example of an image editing model style clip where the text is a person with purple hair. And here is another model, which is a stable diffusion based model, instruct pix to pix. Here the text is turned it into a still from Western. Interestingly, both of these models rely on clip as a text encoder. And if there is a bias in the clip, especially in the text encoder, it can unfortunately lead to the downstream application as image editing. For example, here we are showing you an original image of a woman. Here the prompt is a face of a carpenter, and the model is style clip. And if there is a bias in the clip in the text encoder, then it can lead to a result like this, where we can see there's a goatee for the output image, and this can be very detrimental in the real world, real case scenario. Similar case is true for another model, instruct pix to pix, because it also relies on clip as a text encoder. And here you can see the person's identity has been completely changed from the original one. To investigate whether the bias is coming from the clip model, we can treat clip as a classifier. Here I'm showing an example for the text from a plumber, and if we have a bunch of plumber images and non-plumber images, we can rank these images using that quotient similarity between the text to image features from clip and rank them. And if there is a non-plumber image comes on top and then a plumber image, then we can identify the misranks. So in this way, we can also calculate the precision and recall curve. And here I'm showing you the precision and recall curve for 14 different professions that we have chosen for this study. And we have 1,000 high quality Adobe stock images for all these 14 images. As you can see, the precision recall curve is really low for some of the professions. A careful inspection of these misranks also reveals that the misclassification or the misranks is not uniform across different race and gender combination. For example, plumber females are more misclassified than the males, and for farmer, black or African Americans are more misclassified than white American. And to further investigate where the misclassification is coming from, I'm showing you the GradCam visualization from the clip text encoder for a given prompt. For example, here it is an image of a plumber. We can see for male, it is focusing on the instrument, but for the female, it is focusing on her face, which causes a misrank. And similar is true for other misranks, as we have shown in the paper and supplementary material. Now, let's come to the topic of how we can debias. Now that we have successfully identified the biases coming from the text encoder from clip, a natural way to debias would be debias the text encoder or text output. And it turns out in the literature, there's a very simple way to do it. So if we have a text feature, which here we call text direction, we can find the textual features or text directions for the common race and gender, which we can calculate using the principal component analysis. And for the sake of time, I'm going to discuss here. We explain this in our supplementary material. We can find this gender and race subspace, and we can find the orthogonal direction to it. And essentially what it is doing, it's taking out the components of the race and gender. And this way we're getting race and gender neutral words or the sentences. And using this simple technique, turns out it works very well for the gender biases. For example, face of a carpenter, we are successfully able to debias it for the given prompt. Unfortunately, the same technique is not universally applicable. For example, here I'm showing an image where the prompt is the face of a software developer, and you can see from the output how further is the identity of the generated image from the original image. And it turns out no combination of gender, race, or both subspace gives us good results. And this is also true for complex images such as shown here, and where there is a lot of changes for attires in the background, and the text-based debiasing simply doesn't work. So this leads us to our proposed technique called gradient-based debiasing. So in gradient-based debiasing, we first extract the identity from the original image and the generated image using any popular facial recognition models. Here we use dlib, and then since we have both identities, and we can apply identity preserving losses, for example lpips, which captures the semantic similarity, or id, which captures the id losses. And we also apply clip losses, which capture the text similarity, or even, in other words, the relevancy of the edited image with the given text prompt. So when we use all these losses together, we can backpropagate and optimize this latent. And here the final loss is a combination of all these three losses, where the betas are hyperparameters. After the optimization, we can successfully debias, as I have shown in the generated image. To qualitatively and quantitatively evaluate our approaches, we first choose instruct peaks to peaks, which is a stable diffusion-based model, and we also choose style clip, which is a style again 2-based model, and we pre-train it or train it on two different data sets. One is flicker phase data set called FFHQ, and another is stock occupation high quality data set from our previous WAGB paper, which is called SOHQ. And we also use the images from this data set to evaluate. To quantitatively evaluate the models, we can use the probability distribution of the original image and the generated image and calculate the distance between these two using RMSE, or root mean square. Please note that using such approach does not assume a person's race or gender, because you are not taking the categorical output from the final layer or the prediction from these auxiliary classifiers. And we can also use the classifier prediction scores for authenticity of the original prompt to the generated images. And as you can see, the most of the cases or in all of the cases, our gradient-based approach has the lowest distance from the original and the final identity. And the performance drop in the professional score, as we'll show shortly, does not impact qualitatively as it does for the identity of a person. Now, let's come to the instruct peaks to peaks results. So here we're showing some images and the corresponding prompts, and these are the generated results from instruct peaks to peaks. As we can see, some of the results are quite biased. For example, a person who is a security guard or who is a truck driver, they completely changes the person's identity. And the text-based debiasing here, we can see it's not doing a good job to debias, especially, for example, the security guard. And then our gradient-based debiasing not only keeps the person's identity intact, but it also has the ability to keep the modification as close to the given text prompt as possible, as you can see from the bottom row. Similar results are true for style clip. Here we're showing the results for FFHQ. Results for SOHQ are also similar and shown in the paper and supplementary. Here the generated images are quite biased, as you can see, and the gradient-based approach achieves the best result overall. So in conclusion, in this work, we have discovered biases in clip-based image editing. We mitigated these biases without retraining clip or the generative model. Our debiasing framework does not depend on any specific model or architecture. For example, here are some other queries that are not profession related, but our debiasing approach can successfully debias. And in future, we can include handling complex cases such as biases involving multiple people or objects. If you guys have any question, please feel free to attend our oral presentation and visit our poster. Thanks a lot.